We can do our best, so it's not going to be a perfect argument, but we can do our best in the following sense. The common mistake is actually not by looking at it and conclude, and the common mistake comes in the following the part. Errors, as we partition in smaller and smaller pieces, you quite clearly see errors getting smaller and smaller, right? Errors are small, but there are so many error terms, right? Does that make sense? If you chop it up, each individual quantity becomes very, very small, but there are so many of them, right? So for example, if my error term is 1 over n, and n is the number of partitions that we're dealing with, and this is very small, right? If n is large. But there are n error terms. Suppose that's the number of terms. Then if n is big, then there are lots of terms, right? So let's go ahead and sum up all the errors. What's going to happen? Well, errors are very, very small. As you partition more and more, what happens? Becomes almost zero, right? So we have a tendency that all the errors are almost zero. So can't we conclude that that approaches zero from that information? But it is not so, because all the errors has exactly the same size, called 1 over n, and there are n many of them, right? So what happens? There's no k in there, so you're adding 1 over n, and 1 over n how many times? N times. And what is the answer? N times 1 over n, right? That's 1. So although errors are very, very, very small, as you add many errors, that doesn't necessarily mean zero. It could be some significant quantity, right? So when you look at the Riemann sum and claim that this is a good approximation, what you have to be careful is particularly this part in here. And at this stage, it's very difficult to get rid of our relying a little bit on the visualization. So we're going to assume it is not this too crazy, but we're going to be at least being a little bit careful about not arguing like this. Errors are small, therefore they add up to insignificant amount. That's not true in here, right? That's especially true in here. If you look at each of the segment, the errors are very small, but when you add up, the difference is exactly 1 here, 2 and 1, right? So that's exactly the same type of phenomena. So let me show you that one way to look at the Riemann sum so this is not going to be the general continuous function graph, but it's a simpler shape, so-called monotone function. Monotone function means functions just keep going up or going down. It's not like going up and down, repeating it, right? So like, is the sine function a monotone function? The function value go up and down is not monotone, but y equals 3x, that's a monotone function. It's always increasing. Y equals negative 4x, there's always decreasing. That's a kind of monotone function. So here's the thing, that the way that we calculate the Riemann sum, for example, if I have a function like this, a to b, so we divide it into many different pieces, right? And this is our division, where this is xk minus 1 and this is xk, right? And if you use the right Riemann sum, the tall rectangle is the area. How do you summarize this area? Delta x times f of xk, is that right? If I use the right Riemann sum, that's the height of this rectangle, correct? And the second one would be the left Riemann sum that looks like this. So I'm going to be putting it out right next to it. The area of this one is delta x width times f of xk minus 1, right? That's what that is. And you can see the actual area is this one. So the error in this part is this much of error under calculation, right? If you look at this part, and that we're missing just about this much in here. Let me use a different color. This over calculation is under calculation. Does that make sense? So this also is supposed to define the area. But now I rely on the visualization. If you look at this region right there, without actually defining the area of the region, we can clearly see in this picture using this monotone property that area, whatever, however is defined, must follow the following principle. That must be smaller than this tall rectangle and greater than this bigger rectangle, right? So the error of these two things is measured on by this the rectangle right here, this difference of rectangle. Okay, so that's the error amount that is associated to it. So the big rectangle and smaller rectangle is kind of supposed to be approximation of the actual area, but they're differ by that much of the quantity. So I'm going to slide this one over here, parallel horizontal move to that, right? And that width here is a delta x. Does that make sense? There's one block shifted and then stack them there. So if I go to the next one, if I go to the next one like this, and then there will be, because it's a monotone, it starts from right here, right? And goes to the next one. The difference will be the next block will be, if you slide this one along the horizontal line, it's going to be without overlap, exactly going to be stacked up to the next one. Because of the what property of a function? Monotone property of a function. Functions keep increasing, so from xk minus 1 to xk, higher and higher. So that's exactly stacked up like this. So if you look at all of these blocks, they're all in different sizes and height, but they're all stacked up perfectly, starting from here and all the way to there, right? Without overlap, the errors are all stacked up nicely over this region here, right? So this is, the errors are nicely visualized, no overlap or anything. So this one would be FP minus FA. Is that right, according to that picture? The select of all the errors, which is what I'm calculating here. The difference of all the error is nicely visualized here, and multiplied by the area is the error, and is always delta x, right? As we do the further and further partition, does this change? This guy never changes, right? FP minus FA never changes. But delta x gets smaller. Is that right? Therefore, I show that, I visualize that those error terms we should be worried about is visualized to approach 0. So this explains that little thing here is the error term. There are many, many of them, but you don't have to worry about it. That's the insignificant part. Okay? Not by looking at it here, going through some ingenious argument of visualizing what happened to the error term. But if you go here, then it doesn't work, right? Whatever the attempt to show that the error term approaches 0 should be false because it's actually different. Okay? So we have to do something like that when you define this geometry argument. You have to explain this is actually a good one. So I'm going to attempt that to the arc length, which is the problem in here, right? And because of the fractal shape, it is appearing in two-dimensional world, it's actually very difficult to actually do it perfectly like this. So it's just going to be a little bit better than just look at it. Hey, it looks like approximation. Therefore, that's the good approximation. That's not really good. So I'm going to do something about it. So here is really length of a curve for the following setting: y equals f of x. All right. The graph of a function is given, and we're about to define. Right? How did we define the area of a region? By Riemann sum, right? That was the very definition of the Riemann sum. We used the Riemann sum to define the area of the region. And I did not define the volume of a definition of a volume, right? We just use the cross-section as a definition, a special case. So the idea is like this. So this is a simple shape. Of course, we can't deal with a complicated shape. And an example of complicated shape is like this. The bottom red one, which if you zoom in, and it reveals actual nature. And so we assume that however you zoom in, it always looks like this. There's no surprises up and down and things like that. So that's a sloppy, and that's why it's not a very good one. But at least it's better than just, errors summed up. Errors small, therefore it's approaching 0. At least to avoid that. For A to B, and we're thinking about approximating the length of this arc. At the same time, I explained this approximation is good. Let me go back to this area. Do you think our Riemann sum, for example, left Riemann sum or right Riemann sum approximation is a good definition? Yes, it's a good definition because I explained it here. The one that we leave out from our picture is actually approaching insignificant. I explained that. That's why the Riemann sum is a good approximation, right? So I'm about to do the same thing. So the partition goes like this. You know, it doesn't have to be irregular partition, right? Where I'm just calculating. Don't make things difficult. So we have lots of division in there. And if you look at this point above, and then you have lots of things. The idea is that if you zoom in, and we will have this point, 2 points coming from xk minus 1 down there coming from xk, right? That's the situation. I'm exaggerating a little bit here like that with the curvature introduced. The idea is that they wanted to approximate this arc length, which is very, very close to each other. But if you zoom in, it looks almost like a flat line. We're approximating that with the straight line. Okay, obviously there is a gap, right? But if it's very, very small, the error is very, very small. Almost a zero quantity. That's what we're talking about, right? But there are many, many, many of them. So if you add them together, what's going to happen? Is that going to be zero? And that's the thing that you have to be careful, right? So that's what I'm about to argue. If you look back, I didn't really calculate the error. I just deal with the maximum possibility of error, right? This box is not the really error term. It's the maximum possibility of the error term. So that approaches zero. So that's what we're going to look at. I'm going to come up with some measurable thing that looks like longer than this one, some measurable thing that looks like a smaller than that one, and explain it. But if I connect from here to there by straight line, isn't that the example of always the shortest path from one point to another? So I automatically have this arc length we're actually approximating is smaller than that straight line. Good? I just have to come up with something that is longer and is easy to see, easy to calculate, and you agree that it looks like a longer. So it's a bit of a sloppy argument, but we got to try to do a little bit better than this error just sum up to zero, right? So here's the idea. Then it's a differentiable function, and of course we look at differential function. This is, what kind of line is this one called? Do you know the name of this line if I start like that? At that point, does it look like a tangent line at x equals 1? So it's a tangent line there. So we can calculate the length of this line, right? Straight path. So I'd like to compare the length of this line with this curved part. And I'd like to argue a little bit of that. This is actually bigger than the other guy. Okay? So if you do another, if it is increasing like a monotone function, a differentiable like that, then you might agree that another tangent line there, if you draw it here like that, if you look at the sum of these two a and b in there, and I'd like to argue that the sum of this a and b is actually longer than the arc length there by stretching that, pointing it like that. So you can still argue, I don't understand, explain further why this is longer, and probably I'm going to back down and being unable to explain. But it's here I'm relying a little bit of a visualization, right? And most of the cases, and then b is usually the smaller than this length in here. All right, so that's longer. So I'm going to put that c here. I'd like to argue that a plus c is greater than a plus b. So therefore, calculating this is a good upper bound, something that is greater than arc length in here, and then this one is the shorter. Okay. So I'm going to calculate this sum of these red lines and realize that looks a lot like a sum of the longer line. Therefore, these two things are, as you refine further and further, it becomes the same thing. Right, let me go back and explain this idea with the Riemann sum, the original thing in there. Where is it? And here. So if you use the right Riemann sum, and then we go like this, f of x k delta x. That looks like a right Riemann sum, right? How does the left Riemann sum look like? F of x k minus 1, we used this left Riemann sum in here, and that's delta x k. This one is smaller than that one because the function is monotone, is increasing, right? But both of them approaches the same number called if it is a continuous function, right? These two things, there's a strict inequality because it's monotone. If it's continuous, the theorem of integrable function, right? Theorem of integrable function tells you that this one exists. No matter what xk star you choose, left endpoint, right endpoint, midpoint, some arbitrary point, they all go to the same value. That is the same in the theorem of integrable function. So here, just do the same thing, then we'll show that one and that one looks like a very similar looking Riemann sum, and they're supposed to go to the same value because of the theorem of Riemann integrable function, right? So that's the idea. Okay, so sum of the red segment, the short line segments, right? Okay. So it looks like this. Here's xk minus 1, and here's xk, and here's straight line, that's a red segment. Let me go ahead and do that actually in red. Like that. And I'm not even bothering to sketching the curve, so let me use this dot dot dot. I don't know, I don't care how it looks like. What I'm calculating this length right there, right? So that one has y coordinate. What do you think the y coordinate of that one is? Right, f of xk. Very good. It's rising. These points are coming from the function values, so if xk is the correct one. What about the y coordinate down there? F of xk minus 1 there, right? Okay, so this one is usually denoted, if I write y equals f of x, y represent the function value of x, this is usually denoted by delta y, and here's usual notation of delta x. Delta x never changes, right? So always throughout the interval, but it becomes smaller and smaller. But over the one given partition, this doesn't change. But delta y changes, right? You can imagine functions values changing. So sometimes it's small and sometimes it's relatively farther stretched apart. All right, so let's compute that length. I'm going to call that diagonal length L. Okay, so what is length L? What theorem? Pythagorean theorem, right? Pythagorean theorem says this is right triangle and denominator, no, there's two legs. This is base, square root of base squared, is that right? Square root of the height of this right triangle, correct? Delta x is good. I think I was wrong. This should be delta yk maybe. That gives you an idea. But it actually changes. Delta x, there's no k suggesting given 1000 division, no matter where you look at, they're always the same. So I'm going to put k in there. Is that right? This is really a notation of delta y and subscript to k, not yk delta. All right? So that's that segment. So the sum of the total sum would be, how many intervals are there? N, whatever that n is, right? And those are the segments there. So it's square root of delta x squared and delta yk squared in there. Okay? That's it. That was that simple. If you can rewrite this one as a Riemann sum, then we have a way to calculate this one, right? As n approaches infinity. Riemann sum usually have far to the right. What do you write in the Riemann sum? Far to the right. Delta x, right? So that's the motivation. I want delta x out there. So do you see delta x appearing there? Delta x is right here, right? So if you factor that outside the square root, that becomes just delta x, right? Because delta x. So I factor that out. Do this. Delta x squared factored out. Then what happened inside? Delta x squared factored out is 1. What about here? There's no delta x squared, right? Then what do? You put in the denominator, right? It's delta yk squared divided by delta x. Look about right? Why am I factoring this delta x squared? Because I want delta x outside, like Riemann sum. So square root and delta x squared becomes just the delta x. So delta x is a positive, right? It's a positive, so that goes. Did you know that in general, if I have a squared inside and square root outside, this is not a. Did you know that? This is incorrect in general. Absolute value of this is correct. A can be negative inside, then go through a square, and being positive, square root of inside, everything is fine. But the whole thing is not -1, it's still +1. So this is a correct answer in general, right? But we know delta x is a positive number, therefore it's just going to be positive, right? So the delta x goes outside like that, and square root of what's left here is a delta x. I forgot, I factor out delta x squared, so you have to have a delta x squared down there, right? Okay, you can see it. So this is 1 plus, without parentheses, 1 plus delta yk squared delta xk delta x squared, and delta x outside, right? What is our goal now? I got this delta x, and we have to write this one in the form of some function with x in terms of xk star, right? Xk star. That's our goal. If I accomplish everything in terms of one xk star, then it's going to be Riemann sum. Then we have a formula for arc length. Good? So let's attempt that. Is this mainly this part? If I can write that part in terms of delta xk, so separate it and consider delta yk and delta x in the denominator. That was actually have a square, but both squared. So if I can write this one is simply squared inside, right? So subtracting that. So let me show you what this one is. Who remembers about delta x? What delta x is? Go back. Delta x is this amount, right? So is that right? It's xk minus 1. Correct? How about delta yk? It was this one in here, right? It could have been negative, but it sits inside the square part, so you don't have to worry about delta y being negative or anything, right? So what is it? F of xk minus f of xk minus 1. This is exactly the setting that we recently looked at. It's a very important theorem in Calc 1. First one is called intermediate value theorem. Next one is called extreme value theorem. It's also important. And third one is this one. What is that called? Some value theorem, right? What is that? Intermediate and extreme and mean value theorem, right? Mean value. It's kind of mean value in there. So what does the mean value theorem says? This measures in the graph of function slope of a secant line, remember? Slope of a secant line like that. A and B. That's the slope of a secant line. And you can find somewhere on the curve whose the slope of a tangent line is exactly parallel. That was the mean value theorem, right? Therefore, its derivative is realized by some value in between A and B, right? What is a good notation? For some value that we know it exists but don't know what it is exactly. An xk accent, right? Accent, I use it maybe tilde last time. Make sense? So I have to explain it where this xk tilde is in the interval, actually inside the interval, that's the part of that statement. Not the boundary, actually within as an interior point, it's realized like that. Make sense? All right. So, well, I wrote this one in terms of that. So I think I did it. The sum now looks like k going from 1 through n, delta 1 plus, what is it? Whole thing is f prime of xk tilde. And we didn't take care of that square, so we have to square it out here, and delta x. What do you say? Good? Does it look like something in terms of, xk star? So set xk star to be what? That special value that takes care of this mean value, the xk tilde. All right? So therefore we know this one approaches as n approaches infinity, right? What happened to that? This becomes limit of Riemann sum, better known as definite integral, right? Going a to b. And that inside all the xk tilde or xk star becomes just regular f, right? Is that correct? And what happened to delta x? Becomes dx. So if you use this red segment right there, the entire sum is well approaching this quantity right there. And I was worried that maybe this is not good. Maybe we're actually looking at bottom black line underneath that red one, and the actual one was 2, right? That's what I was arguing here. So I have to kind of measure that one as well, the long one, right? Make sure this guy, sum of that guy approaches that as well. Then it seems like whatever trapped in between must approach to that according to our some simple principle, right? That together explains that this is a good approximation. Good? Yes. It's a very important idea in mathematics. If you wanted to define something, don't just define it. Somewhat you have to explain that your definition is good. And how do you do that for something that you don't even have a definition? Is that kind of upper bound and lower bound and show that what you're approximating is trapped in between. Therefore, if these two things are going down to one thing, then you're explaining that, hey, that's a good definition if they're convergent. This is called the squeeze theorem. Did you hear about that? Squeeze theorem. If you have two quantities that are controlling below and above, if they have the same behavior, whatever that you're doing is good. That it's explaining nicely. So let's go back and approximate this guy in here, right? This is a lot easier. It is immediately, it's there. So blue segment, is that right? Yeah. Sum of the blue segment. Okay? So that one looks like this, and there is just 2 points with xk minus 1, xk, and there's this whole thing, and it is not really coming from function value. What was this line here? What's this line with the... We know slope easily. That was a tangent line, right? So slope of a tangent line, how do you calculate that? Right, but you have to do the limit, right? You have to do the limit. That's the slope of a tangent line. So if you do the limit, right, the slope of a tangent line will be, the value will be f prime, is that right? At where? This is the key. So let's go back to tangent line. Where is the tangent line defined here? Where did I draw that? Right here. That's where I draw the tangent line, right? So what do you plug in to the derivative? That point right there, xk minus 1. Does that make sense? Xk minus 1. Xk minus 1. All right, so we know the slope. We know this guy. What is that? Delta x? If you know the slope, what would be that one? This I'm going to call delta h maybe. A little height. It's not delta y, right? Actual function value is down there, remember? Right. So what is that delta h? If I know the slope. Right? So delta h divided by delta x is supposed to be slope, right? The slope is f prime of xk minus 1. Is that right? So from there we can solve it. Oh, that height, delta h, is exactly f prime of xk minus 1 times delta x. All right? So we got that h. So let's estimate this one. That's going to be not L, well, with the longer one, so it's going to be delta capital L. How about that? All right? So let's sum up. The sum is all that delta LK, the hypotenuse, right? So with k going from 1 through n. So let's use Pythagorean theorem again. So let's take one step at a time. It's delta LK is this one in here, and using Pythagorean theorem, right? So again, so bottom was delta x squared. What about this one in here? Delta h is this one, so is a delta h squared is now f prime of xk minus 1 squared times delta x squared. Is that right? Since delta h is look like this. Good? Let's keep that. Was the delta x squared plus delta h squared. Right? That was this delta x and this delta h. Delta h is now written in terms of the value of a derivative like this. So we substitute it back. So inside in here, the whole thing is replaced like this. Delta x squared plus f prime, f prime of xk minus 1 in there, delta x squared outside, and all that sum. All right? Make sense? So we want to write it as a Riemann sum again. So we pull out delta x squared. This time there is delta x squared everywhere, right? You pull it out, and you're left with 1 plus f prime of xk minus 1, and all the way, times delta x out there. Is that good? So, does it look like a Riemann sum now? Delta x is out there. Everything here is written in terms of xk minus 1, right? Whatever the point inside in terms of one variable, it's true. Okay. So, where does that approach as n approaches infinity? The definite integral, right? Going from a to b, the beginning and the end point of the interval, and root, the 1, that whatever that xk star that we're using becomes just plain x. Prime is there, it's very small, and dx. So if you sum up the longer one, that it becomes more and more this number, right? But that is actually coming from slightly longer version, and the shorter version was on this one as well. So let me go ahead and circle that. And down here, upper ones also approaching this shape. Looks a lot like it, right? In fact, they're exactly equal to each other, right? Good? Does it look like a squeeze theorem? So here's the sum of, let me use a different color. Sum of red segment, right? And here's the sum of blue segment. But actually in between, there's the actual guy, actual length. If it is somebody defined it for us, and if that's a good definition, is always trapped in between the red sum of red segment and sum of blue segments, right? And we show that these two things are going where? Exactly same value, called this guy, blah, 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 dx. Summarize it in there. So by squeeze theorem, this actual length that we define must be that value there. So this whole argument kind of explains this actually good definition. That what we come up with is connecting these 2 points of that thing is actually a good approximation. All right. So I want you to write that down, that the common value and accepted as a good definition of a good in parenthesis, good definition of a arc length of the graph of a function over a to b. And remember that this picture in here, where is this root 1 plus f prime of x come from? What is this structure really due to? Square root of a plus b, that come from Pythagorean theorem, right? So that really helps you to remember the formula. It's coming from Pythagorean theorem, so we've got to have a square root in there, right? So it's really delta x here and delta x times f prime of x, and the slope of this one is f prime. Just sloppy summary of what the careful calculation we just did is summarize it here, right here. Bottom is delta x, slope is kind of f prime of x, and this side must be delta x times f prime of x. Pythagorean theorem, according to Pythagorean theorem, the hypotenuse is exactly delta x times root of 1 plus f prime of x squared. Does that help you to remember the formula? So what's inside in here? The length of a hypotenuse is the rectangle we looked at. All right. So we did the same thing when we did cross-section, look at the formula, especially when we look at the shell method. What was the meaning of inside the shell method formula? Circumference times the height of the cylinder, right? Exactly. So like that, we made that attempt. So I'm going to save this one.